All right, so any questions about the course in general? Otherwise, we'll just move on with the lectures, okay? Okay, so let's now talk about recap. Let's do a recap, as usual. So last time, we actually continue with the discussion about formulating strings over here, okay? So that's where we were. So we talk about sigma k would be the set of strings of particular length k, and also plus would be all the non-empty string, basically, altogether. And sigma star would be all the strings you can construct from this particular alphabet, including empty string. Okay, so that's so these are the three notations you really want to get used to, and also how you can specify them accordingly using set comprehension notation, right? So far we have seen quite a bit of examples to really use a set comprehension to denote different sets that we want to express. And today, hopefully, we'll definitely finish regular expression, and then we'll get into DFA. In which case, it would be also very handy to really use the set comprehension notation to express what a DFA is. Okay, that's something we'll also talk about, especially we want to define a set of strings like a language formally. We'll get there. All right, so that's something we spoke about last time, and that one there is just about review about using for all and exist. Since for the set comprehension notation, the second part over here, after the vertical bar, let's say this part over here is really about specifying some predicates, which will evaluate to either true or false. So using for all will exist will be very reasonable if you need it, right? So you can go over that as well. And as I promised, I'm going to make some background slides just to review a little bit about propositional logic, predicate logic, and also sets and relation. You also need those kind of stuff to really understand the formulation for DFA, NFA, and also later on when we talk about parsing, right? So these are all the logical stuff you guys learned maybe many years ago, but it will be necessary for the understanding and of course for the subsequent test. I'll make the slides available later. All right, so also we did some exercises just about if you got some set of strings of particular length, how do we figure out, number one, how large the set is, how many strings are there, and also how we can systematically enumerate all the members in the set. Okay, that's something I will spoke about, and this will be just some relationship between the alphabets and string. You guys can give a try on that particular proof. If you want me to go over with the answer together, just drop by office hour and we'll talk about it. All right, so far it's about the strings, which we finished last time. And then we go ahead and talk about language. It is very important for you to really understand this particular diagram over here. So when you talk about sigma star, think about it's just any arbitrary sequence of characters that you draw from a particular alphabet, like arbitrary input. However, for the language, it's more like it's more like a desirable set you want to define for your problem. So you want to make sure the language here is more well-defined about what exactly are the strings that you need. I think the best example for you to make would be, think about sigma star over here is the set of, is all the strings you can type on the keyboard. Anything you can type on the text editor. However, not necessarily everything you type on the keyboard is going to be qualified as a Java program that's going to compile. Right? So you can think about the Java program that compiles is a language. Anything you can actually type from the keyboard will be sigma star. Right? Definitely, you can find some string over here that you type from the keyboard that simply maybe just not very useful. It simply doesn't compile, or simply contains symbols that would not even pass maybe the lexical check. Right? Right? Think about this kind of a relationship, between the mathematical concept and to what you know about in programming. All right, and then we did a little bit more exercises about this one here, right? So these are very different, right? We also discussed them last time. You can also review to see how they're different. And finally, we define problems. You can think about the compilation problem we're trying to solve in this course is somehow you want to implement this membership over here. So your compiler is going to take some arbitrary input that can be drawn from some particular alphabet. Let's say the input is going to be some sequence of characters that user can type, from the keyboard, let's say. And then you want to make sure your compiler is going to going to compile with respect to a certain language in your mind. And that one there is going to be according to the project description that's going to be released after the reading week, right? And speaking of the project, so just want to remind you every week, maybe you want to meet with your fellow student in person in class and think about who you actually want to work with together for your project. Got to be at least 2 people in the team, or it can be 3 maximum, either 2 or 3, no more, no less. Okay. All right, so really think about this visualization here. I think that's really important, right? To understand language, problem, and string. And we move on to talk about regular expression. So that's the first notation we're going to learn to recognize regular languages. So when you're only doing the lexical analysis, you're only dealing with string satisfying certain pattern. If they satisfy a certain pattern, we call them tokens, right, in the lexical stage. So we got union, straightforward. I'm not going to bother you again. Concatenation. So this is important. What does it really mean when you try to concatenate 2 languages, language L and language N? That means you can draw some string from L and draw some string from N, and then concatenate them together, and all such concatenation will be included in when we concatenate the two languages together. Right? So that's a formal definition. Right? Look at this set comprehension in here. It's very concise and precise to tell you what the concatenation of 2 languages are. Okay? And then the last thing that we spoke about last time was clinical closure. In some way, we have to really use the language concatenation over here. It's just that rather than L concatenate with N, presumably there might be different languages, but now we are going to say L concatenated with L for as many times as you like. You can think about every time you want to do one more concatenation, that means one more repetition. So that's really what star means. Star simply means as many concatenation as you like. Right? So let me start from this page. I want to make a little bit more annotation. And we'll talk about definition here. But just before that, let me just go there. Okay? I'll just kind of make a duplicate here. So think about if you do any, if you think about L star. First of all, L star over here, by definition, is just about as many concatenation as you like, including no concatenation. As many concatenation or repetition as needed, including no concatenation or no repetition. All right, so this is something I didn't really mention, but hopefully that's kind of obvious to you. For example, if you look at as part of the L star, we got actually contain L to the power of 0. What does that mean? That means we simply don't want any concatenation. When you actually don't have any concatenation, well, think about that by definition. Okay. Oh, actually, you know what? Let me just refer to this. I think that'll be a bit easier. I don't need a separate line. When we got only a single concatenation, it will just be some string that's chosen from L. If you say L and then no concatenation, that simply means this part over here is just empty. Empty means you have no concatenation, so it's as if no string has been created. But it's not really empty set. It's just a string with 0 length. So think about this one here, the epsilon over here. This is a string resulted from 0 concatenation. 0 concatenation, right? I think this one might be the trickiest one to kind of understand. Just make sure you understand it's not really empty set. It's a singleton set with just empty string. And then we spoke about L1, L2, all the way to Li. I can be an arbitrary number. And then if you look back to the slides, we say that L star over here is going to be all the different possibility of concatenation union together, right? So we got as many concatenation as you like. And let's do very quick 2 exercises together. Number 1, what is the cardinality of Li? So actually we got Li right here, right? So hopefully that's also very straightforward to you, but let's take a look, right? Okay, Li over here. So question number 1. What is the cardinality of Li? Basically, this one is saying somehow you want to get I concatenation of the same language. For each component over here, how many possibilities are there for you to choose? For example, x1 here, it should be chosen from just L. So you got the cardinality of L possibility, right, to choose. All right? So this one here should be equal to, for x1 is going to be just L. So this is how many strings you can choose for x1, multiplied by, and also the cardinality of L, since we are trying to concatenate L with itself. And that one there will be how many strings you can choose for x2, right? I'm just following x1, x2, all the way to xi, right? Because each one of them can just be chosen from the same language. And if you simplify that, we just multiply the same number I times, right? So that would be L to the power of I. All right, so that's the answer. Okay. All right. And the next review question here. Given that L, the language here, is 0 to the power star. Okay, let's see that. Okay, and what is L star? Okay. Okay, let me write down the question first, and then we'll discuss that. Okay, question number 2. Up here. Given that L is 0 star. And this is actually a notation that we did last time, right? If you only think about 0 over here is an alphabet. So we are having some alphabets that contains only one symbol, which is just 0. And then if you try to recall about star over here, that means it could be length 0, length 1, length 2, all the way to length infinity, right? So this will be just as many 0 as you like. This will be just simply, what should we start with if you want to enumerate somehow? What will be the shortest string? Would that be just a single 0 or something shorter? Empty string, exactly, yeah. Epsilon, 0, 0, 0, and etc., right? As many 0 as you like. It's like an infinite set. Okay? Let's say I was just trying to give you a little bit more context about the question. Given that L looks like this, here's a question. What is L star? I think that this exercise here, the answer itself is actually not too difficult to grasp. The reason I put it here is you can see we also got star here. You can see we got star over here. We also got star over here. That could seem confusing. The star here is actually used in different contexts. The star here is about a set of strings of length. Oh, sorry. This will be the set of strings that's going to be of certain length based on the alphabet. And this one here is going to be a set of concatenations based on the language, right? It's different. Okay, I'll just disambiguate that very quickly. This will be all the strings of arbitrary length. Sorry, here ARBI just arbitrary, right? Just didn't have space to spell it out. So these are all the strings with arbitrary length. On the other hand, this one here will be all the strings resulted from arbitrary number of concatenation from the language. Strings from arbitrary number of concatenation. Because the base over here, this is alphabet and this is language, right? So guys, I think that's the main point about this exercise here that I want you to watch out for. Okay? Okay, if you don't mind, I'll just do one more annotation just to make it a little bit even more clear for you. Think about this guy here. It's like an alphabet. Versus this guy over here is a language. That's why they should be interpreted differently. All right, so now the question is, what is L star? L star, well, we know that L itself is actually like infinite, right? And then if you want to concatenate L for as many times as you like, itself will also be infinite. But what exactly is that? Yeah?
Is it just the definition of Li?
Li, but what's I here? Because you don't really know what I is. I is more like an intermediate value you kind of use to really define L star, right? So because I could be 0, can be 1, can be 2, can be infinity, right? Yeah. So what about L star, right? Okay, here is how I can, you can think of it intuitively, okay. L here is simply basically any combination of zeros, really. Once could be 0 zeros, could be 1 0, 2 zeros, etc. Basically just zero, bunch of zeros. And now you're saying you take a bunch of 0 and concatenate with another bunch of 0. What do you get? You still get a bunch of 0.
Oh, so they're all still the same language.
It's the same language, really. That's kind of interesting, right? So this guy here turns out L star is simply equal to L. Okay? But this equation here is not necessarily true for any language. Somehow this language here contains only 0. So that's okay. Not true in general. Okay, so that's why we just want to do this exercise here. Point number 1, you see the exponent over here in the context of the base being the alphabet or the base being the language. That's point number 1. And point number 2, because of the uniqueness of this language over here, even if you try to do multiple concatenation, you still got the same language. You just get a bunch of zeros, basically. Okay, yeah. So this one here, not necessarily true for arbitrary L. That's something you want to note. Not necessarily. True for any L. All right. All right, so that's about the cleaning star. So far we have covered 3 language operations. We have covered union, we have covered concatenation, and we have covered cleaning closure or cleaning star. And the next step is we're going to see different regular expression operators and operations. And the way we're going to define their meaning or semantics is by using operations. Okay, I'll write it down here. That's something we're going to define. Oh, actually it's here. Okay, so think about, so we're going to actually talk about the meaning. The meaning of each regular expression. Well, here I simply said RE. So RE I also meant regular expression. Okay? So the meaning of each regular expression operation is defined formally by its corresponding language. Just one thing I want to show to you. For example, if you look at, for example, this one here. The plus over here is a regular expression, language operation. Okay, so this one here is an RE, regular expression operator. Okay, just the plus. Okay, and then this operator over here, how do we define its meaning? So given some, the way you define it is like a recursive, right? You guys know pretty well what a recursive operation is. So if I got some regular expression E, I got some regular expression F, I can simply combine them using plus, so I can get a larger regular expression. The way to define the formal meaning for this plus operation is by saying, what would be the language associated with this particular regular expression operation? Okay. So the L over here is going to define the meaning. So you already want to refer to L right here, right, about the meaning. Okay, we're going to do this for every individual regular expression operator. Okay, how many operators do we have? So we got plus, We got also concatenation. We got some regular expression E, some regular expression F, and we got some concatenation. We just put them one after the other. So the order matters. And then we got E star. I'm pretty sure for those of you who actually use some regular expression from Java, maybe from Python, I'm pretty sure you use star all the time, right? Just to say the pattern may be repeated for as many times as you like, including 0 time. And the final one, we can also use a parenthesis to kind of force the order of the evaluation. Pretty much like arithmetic, right? Okay. Let's now try to look at, so these are the recursive case, right? So these are the recursive case for regular expression. Let's now define them very quickly, and then we can look at the base cases. Okay. Pretty much like how you think about recursive method, right? If you want to solve something recursively, you can, I would say whether you kind of start with the recursive case or start with the base case, it doesn't really matter. But for now, let's say we do the recursive case first. Okay, just a bit more straightforward. So the first operation for regular expression, if I say E plus F, basically I'm saying that I know that there is a way to figure out what's the language of, what's the language of the E. And what's the language for F? Think about we're defining this L here like a recursive method. If I want to apply L into E plus F, what I can do is divide and concur. I can say apply L into E first, and then L into F, and then how do I combine these two? Because I know that the language of E and the language of F, these are individual languages. What kind of language operations can we use? We can either use union, or we can use concatenation, or we can use a cleaning star. Right? So now in this case, we can simply use union. All right? Let me just go a little bit deeper. Think about what we're doing here. This plus over here is a regular expression operator. Somehow its formal meaning can be transformed into the union operator for regular languages. Okay? That's really what we're doing. We're doing something very formal. We are trying to define the formal meaning or formal semantics for regular expression. Okay? This one's straightforward. And this one here, actually no surprise. If I somehow want to define what's a concatenation of regular expression E followed by regular expression F, I can first of all divide and concur. I can first of all figure out what's L of E. And also I can figure out what's L of F. How do I combine them together to make the formal meaning for concatenation? Well, I just concatenate these two languages together. All right? And we learned about how to concatenate language operations before. Okay? So, one more note. EF over here is the concatenation for regular expression. This will be the concatenation of regular expression. On the other hand, this one over here, L of E followed by L of F, that will be the concatenation, but of languages, regular languages, like a set of strings, basically. Yeah. This might be something maybe you used to see in 2001, but now just seeing that again, maybe from a different angle, I think hopefully you will get it, right? These are kind of nice theoretical foundation, for the compiler, lexer. All right, this one here, again, no surprise. This will be the cleaning star on regular expression. It would be just the corresponding L of E over here, and then star. Okay, so this is the cleaning closure for. This is the cleaning closure for regular languages. And this is the cleaning closure for regular expression. Okay. Regular expression. Okay. The final one there, this one here just kind of tell you that if you simply put some parentheses to force the order of evaluation, you haven't really changed the nature of the language that's associated with it. So this one here, straightforward, it will just be the L of E. Okay, like that. Yeah, you will see the full definition on the slide. I just want to work it out, from scratch together with you, so you can see a little bit more about what's really going on here. So these are the recursive cases. Let's look at base case. So recursive case, you can always make some recursive call, right? L on E and also L on F. But now, if you look at the base cases, let's see what we can do. So the simplest regular expression you can write will be just empty string, theoretically. So that, well, in practice, just don't write anything. That means that matches nothing, right? So this will be the smallest regular expression you can write. This will be the shortest. How about that? Shortest regular expression you can write. Okay. You can also write another regular expression over here that's simply just empty.
Where's the longest root?
There's no longest. It can be, in theory, it can be infinitely long, right? Regular expression is just a sequence of characters. It can be infinitely long. Yeah. All right, so empty set over here is also, for our discussion, we also talk about empty set here can also be a regular expression. Okay, let's see the corresponding language. So in the case you write epsilon, that means you have a single language where the language contains only a single string, which is empty string. Okay? So this one here is a singleton language. With just epsilon. On the other hand, if you actually write as a regular expression, just empty set, in which case you got an empty language. You don't even have a singleton language, just an empty language. Okay, so this one here is just an empty language. Right, so these are the two extreme cases, and one more. So let's say, this is to say, if you actually got an alphabets. If you got an alphabet sigma, and then let's say somehow the alphabet will just be maybe A and then something else, right? Just not empty. If A is simply one of the symbols you can use from the alphabets, what if you just put A as a regular expression? That means match that character verbatim. Okay. This means to match verbatim. And the language there, not surprisingly, is going to be also a singleton language. But the language there contains just the string A. You only match that. Okay, it's going to match just the string A of length 1. All right? We're good so far? All right, so these are the regular expression languages, and then let's now try to look at some exercises, which would be a lot of fun to actually work out. Yes?
Would the language that contains A not also contain epsilon?
No, that one wouldn't. You mean this one here, right? You mean this one specifically, right? Okay, let's talk about it specifically. If I got, for example, L of A. So we say that this one here is only going to input string A can be matched successfully. Can be recognized, how about that? Since we say recognized, can be recognized. So actually, I'll give you both. Either it can be matched or it can be recognized. Any other string, including the empty string, cannot be matched by just the pattern A. Okay? So that one there, you would say that's simply equal to just this A here. And it is important to say that epsilon, empty string, is not a member of the language of A. Also, you can say that B here, assuming that B is in the alphabet, okay? is also not a member of the language of A. Also, AA is not a member of L of A. In order to be in this language here, it must match exactly A, just one occurrence. Anything other than A will not just be in the language. All right? So you got 3 other examples here. 1, 2, and 3. Okay. Okay, very nice. Okay, let's look at some examples just to strengthen our understanding. Let's do these examples quickly, and then we'll take a very short break, just about halfway. All right, so let's now look at them one by one, okay? Let's look at just one by one in this kind of sequence, right? We're going to work out exactly what each one of them should be. All right? Let's start with the first one. If I actually got some, let's say this is the, this is a regular expression. Oh, beg your pardon. So this, I think that this one here is still given the language L. Okay, got it. Let's say we got some regular expression here. Let me just see here. Nope, just language operation. So you can think about this one here is just empty language. Let me just double check. Okay, good. Now I know exactly what I wanted to say. Okay. This one here is a regular expression. And then this one here is also a regular expression. Okay? And this one here as well. So what will be the corresponding language we want to know? Turns out this one is pretty easy because we know that the plus here simply correspond to union, right? So that's what we said just earlier. Okay? So this one here is easy to see. So we can say if you got this one here with a regular operator, regular expression operator, L, this one here would just be the union, basically, which would be just L itself. So this one here is going to apply the union operator. That's just going to be L. And this one will also be if you kind of swap the order, because union somehow doesn't matter the order. So it will also be L plus this. Okay, like that. Yes?
So we don't have to write L plus the language of the empty set? L plus L, no?
You mean this one here? So what we are saying, either writing this or writing that or writing that. So these 3 are equivalent. They actually correspond to the same language, really. Because adding the union and also adding the empty language, they don't really make any effects. So you would just boil down into just L itself, because it's union. Right? Whenever you're trying to union with the empty set, it has no effects. Yeah, it boils down to this intuition. Yeah. All right? And then I would suggest we go to this one here, the last. This one here is kind of a little bit more trickier. That one will require a little bit more logical reasoning. I'll get to this, the last. How about this one here? Let's see. Let's say here we got some empty language. And then we are trying to apply the regular expression operator, cleaning star. Okay, so what will be the corresponding language? Okay, so whenever you're given this kind of question here, I would say just apply the definition and unfold it and see what you will see. Okay, so let's now try the following. If I start with the question here, okay, by definition, it's going to be as many concatenation as you like, including no concatenation, right? It's going to be either this one to the power 0, 0 concatenation, or 1 concatenation, or 2 concatenation, etc. Okay? And then, let's see what they will be. Somehow, this one here has to be treated a little bit differently than others. Okay? Somehow, this one here. Versus these ones over here are a little bit different. When the exponent is simply just 0. That's something we saw last time. Okay? When the exponent is simply 0, that means no concatenation. We said that no concatenation doesn't really mean it's empty. That means you got exactly just one empty string, right? No concatenation. That's what we just said in the beginning of today. So this one here is simply no concatenation. That means it's going to correspond to a language with just epsilon inside. No concatenation. Okay? On the other hand, for all the things starting from here, that means we got at least one concatenation, at least. Okay? Let me just take one of them as an example here. Okay? At least one. How do I understand, for example, this one here? Okay? By definition, if I just want to do one concatenation, I'm going to choose some string x over here, and then x will be a member of sigma. Since I know sigma is empty, so x being a member of empty set should be false, always. There's nothing that can be a member of empty set. That one we know pretty well. So this part over here is going to be false. Remember the definition for set comprehension. We want to include all the expression x that's going to satisfy the predicate part. But there's no way to satisfy false. So there'll be no x that can satisfy that. So the resulting set will be no members, just empty. Okay. So this one here will just be empty because no x can satisfy false. Okay, so for that one there, it's going to be actually union empty set. Okay, and then similarly, if you try this one here, very similar. This one here, by definition, I'll just write it down, right, just for completeness, since I already talked about it. This one here is actually going to be actually x1, x2, and then x1 should be in empty set, and also x2 should be in empty set. And apparently you can see there's no way this can be true, and there's no way this can be true, because it's an empty set, right? So overall, we still get a false predicate right here. It's still false. No x1, x2 can satisfy this false predicate. So it would be just empty set, and etc. So, and then this one here. So finally, we're just going to get just the result of empty string, which correspond to the result from 0 concatenation. All right, so that's a little bit trickier, when you talk about the first one. So we say this guy here, finally, is just this guy over here. Okay, like that. Okay. And we can now somehow reuse this result for number 4. Okay, with the number 4 and then with the number 2, right? Number 4 first. For number 4 here, I'll put it aside, right? Number 4, I'll put it here. Let's go by definition again. This number 4 here is about concatenation. We want to concatenate this guy here with this guy here. And for this one here, we already know from this result is simply this. We are reusing it. Okay? That's right on the definition. So we got concatenation between empty set star, empty language star, and also L. This will be, by definition, x1 and x2 should be two parts of the string. The first part should come from x1 should really come from empty star, and the second part should come from L. And we know that this part over here, this part here is right here, the singleton set of empty string. So what does this really boil down into? This one actually is not going to give you anything like a false, like before. No, not really. It simply tells you whatever string you choose as x2 from L is going to be concatenated with some string that's chosen from the singleton set of empty string. So you always choose empty string from here. There's only one possibility you can choose for x1. So you always got epsilon with some x2. Remember we talked about identity before, right? Epsilon is the identity for string concatenation. So you always got x2, always. Okay. Think about x1 here is always epsilon. And you say epsilon x2 is simply just x2. That's the identity. So let me write down one more simplification. And this will just be equal to, basically x1 there, it can just be ignored somehow because it's an empty string. So it's really about x2 such that x2 is in L. And by the way, what is that? We're basically saying we're going to collect all the string from L. It's simply just L, right? All right, so this guy here can be simplified into this. Okay. All right. So now we have done this one here, and this one here. Finally, let's look at this one here. Okay? And then we are done, and we can take a short break. For this one here, I'm going to put it here. Right here. We got empty language concatenated with another language L. Okay? Again, let's go by definition, and then you will see. So what we do is, we're actually going to go from, let me just copy down first. We got empty language concatenated with L, which will be two parts, x1, x2. x1 should be chosen from the left. x2 should be chosen from L. x1 should be chosen from empty. x2 should be chosen from L. Now, what would this be? That's something we have just seen. Any idea? Huh? Empty?
Is it just L again?
Watch out. It will be L if somehow this predicate over here can be reduced into x2 is a member of L. Is it reducible to that? What is this, by the way?
Epsilon?
It's false, right?
It's false, yeah. x1 is a member of empty set. Nothing is a member of empty set. So this part here is going to be false. False and anything will just give you false. Okay, just watch out. Good. All right. So this part over here definitely is going to give you false. And it doesn't really matter what this part is. It could be false, could be true. But when you try to combine that with the conjunction over here, it's going to give you false for sure. So this part here, guaranteed to give you false. So you got a set comprehension notation where the predicate part is actually, again, false. There's no x1, x2 that can satisfy false. So overall, language should be just empty. Okay. So here, this one here, it will just boil down into the empty language.
Like I know that if you try to have a variable
I see what you mean. The reason that this whole thing here is false is because we know that this part is false, and also we're using conjunction. On the other hand, if for whatever reason, if this logical connector here happened to be, for example, OR, in that way, this one here is not going to impact OR too much. You still want to check to see what this is.
So if it's like an empty set plus L, it would still be an L?
Yeah, exactly. Yeah.
Oh, yeah, okay.
Yeah, that's what we saw earlier, right? Yeah. So my point is, this part here is false, we agree. Nothing can be a member of the empty set. However, this part here being false do not necessarily will impact the whole thing to be false, only if you're putting that in the context of conjunction. Okay. All right? Even if you put that into, for example, false, you replace this by imprecation, for example, right? Right? If you guys can recall very quickly, okay, I'll put it here, right? This might be handy as well. I'll put it here, okay? About imprecation. I think for the truth table for conjunction and disjunction, you're pretty good. Well, I'm going to include that review slides, but just for imprecation. Okay? So we got, let's say, P, and also we got Q. Let's say they are propositions, like a Boolean variables. So it could be false, 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 true, true, false, true, true. Okay? Like that. Right? What is P implies Q? How do we fill out the truth table? Right? Why don't we go row by row, first of all, and then I'll give you some insight. Okay? False implies false. True or false? True. Okay. False implies true. True. True implies false. False. And this one here? True. Okay. So the only way to make the implication false is when the antecedent is actually true, but the consequence is false. That's the only way. On the other hand, if you assume the antecedent is true and turns out consequence is also true, you get true. It's like assuming the antecedents. On the other hand, if you got antecedent being false, in some ways it's more like if the assumption is simply false, I don't care anymore. The implication is simply just true. Okay? Yeah, if you want to find a bit more insight, you can also look at a review slide, which I'll make available to you very soon. Right? You can look at that. There's some analogy about thinking about implication is whether or not you are breaching a contract between the promises and also the terms. Right? That's something you can look at that as well. Okay? The way I I don't really memorize the tables. So I always got to think about analogy if I forgot. All right, any questions? All good? All right. Why don't we take a very short break by taking attendance, and then we'll resume. All right, so before the break, we spoke about various things and basically about base cases and also recursive cases for regular expression, right? That's on the slides. But we went over them thoroughly already. And also, we try to solve very carefully about these exercises before the break. So really pay attention to the details to see why they are the way they are. Reach out to me if you want further clarification. Right? Let's now move on. All right. So now, let's say, well, this might be one of the very few regular expression example we're going to do together. But this one is reasonably complicated. But let's see how we can do it. Okay. This might be something you solved before, but let's solve again. So we want to write a regular expression for this language here. Right? So let's now, first of all, make sure we understand what the problem is. Right? As you can see, we try to define a language. So you can think about the whole thing here is a set comprehension that defines a set of strings. So this will be a set of strings. And the whole thing here is a language. And then we say it's going to be all the W such that W satisfy this constraint over here. And here we're just being a little bit more informal, assuming that the English description is kind of very clear. So we say that W, any string that has alternating zeros and ones, should be included. For example, If I say this language here is L, let's say L is equal to this language, right? You can definitely see, for example, 0, 1 is in L. 0, 1, 0 is also in L. Okay. And let's say we also want to say some boundary cases. Epsilon is also in L. We're thinking this way. If you cannot find any violation about alternation, then it's alternating. Okay? This one is here is in L because no violation of alternating. Zeros and ones. Right? Similarly, you can also say 0 is in L. There's no violation. However, if you say 0, 0, no. It's definitely a violation. 0 followed by itself. It's not alternating. Right? Etc. Right? At least try some example just to make sure you understand what the problem is. Yeah, I think for this one, why don't I just kind of present the slide solution somehow? I kind of adapted from some textbook. So I'll just present the solution to you kind of gradually, and then you guys can also give it a try. If you come up with something else, you can share them with me. We can talk. Okay. Let's start with something here. You may start with, for example, 0, 1s. Let's start with this one here. So this one here, what would that be, right? We're saying that 0, 1, you can repeat for as many times as you like, including 0 time. So this one here tells us it's going to be basically epsilon. It can be 0, 1, can be 0, 1, 0, 1, etc. Let's start with that. That's definitely one set you have to cover. And we can cover as many sets as we like and kind of union them together, right? That's the beauty about using the plus operator in regular expression. Well, obviously, if you only got 0, 1, what about 1, 0, right? So you can also try to specify this separately and use union, right? So you can think about, for this one here, you definitely can get 0, 1s, you also get 1, 0s. That one there, symmetrically, is going to cover also epsilon 1, 0, 1, 0, 1, 0, and then etc. We got 2 so far. Okay. However, we actually might be able to do a little bit more. For example, let's see here. You can see, let's say for example, you can see here we got 0, 1. Oh, we got 0, 1, 0, 1, 0, 1. Would it hurt if I only also got 1 here? Right? 1, 0, 1, alternating. 1, 0, 1, 0, 1 is also fine. That means it is okay if I also consider another set where I simply say, whatever this is, I'm going to concatenate it with just 1. I'm just make sure you can also start with 1, right? I'm going to kind of put that separately, okay? So here I'm going to get 1, 0, 1, star. I kind of put it in separately, and then eventually I can union them together or plus them together, okay? This one here is going to be, guys, what is the shortest string I can have in there? 1, okay? Not epsilon, right? I can get 1 here, or I can get 1, 0, 1, or I can get 1, 0, 1, 0, 1, etc. Okay? And let's see, okay, we can get another possibility. Give me one moment. You can see, for example, here, I got 1, 0, 1, 0, 1, 0, right? Would it hurt if I put 1 at the end? Would it hurt? Right? I can put 1 at the end, Also wouldn't hurt. Right? You can see what I'm doing here. So what I would do is I'm going to put it here. So 1, 0, star, and then put 1 at the end. Okay, so that one there is going to be, again, the shortest string will be just 1, right? Can be 1 here, or it can be 1, 0, 1. So 1 repetition of the pattern. Or it can be 1, 0, 1, 0, 1, etc. Right? So these are the 4 possibilities, right? Now, of course, I know the solution already, so I can present to you. But of course, if you are given some problem you haven't seen before, you will just need to work out different possibility, right? What you want to see. Yeah. I do have some exercises on the slide there for you. You can give it a try. Okay. So what we want to do is we want to union them together, but there's no union operation in regular expression. It's when you define a formal meaning for regular expression, you got to use the union. So now if you only want to write regular expression, right, that's what we want to do. Regular expression, we got to use the plus operator. Plus, plus, and plus. So this here is acceptable, nothing wrong. However, since now we are kind of studying some like a best solution, we can somehow do a little bit of we call refactoring. Yeah, but before that, question. Are we missing zeros alone? I think we might have. Let me see. So here we got, yeah, I think you're right. We might need to get 0 as well, because 0 makes, yep.
Maybe we don't need the last one instead. Because the last one.
Yeah, yeah, actually that covered. Oh, pretty good. Thank you. Yeah, I agree. Okay, awesome. Yeah, I kind of demonstrated to you. Sometimes you may come up with something that may not be necessary, right? I appreciate that. Okay, exactly. Good. I appreciate that. Thank you. This one, because guys, you can see that this one here is exactly like that one, so we don't need that. Okay. So what we can do is we can say 0, 1, 0, star. All right. Awesome. I really appreciate the feedback. So this one here is going to be, the shortest one will be 0, and now indeed we got 0 covered. And then it could be 0, 1, 0, 0, 1, 0, 1, 0, etc. Good. Okay. So this long answer here will be acceptable, but we can do a little bit of refactoring. So what do I mean? If you look at some common pattern here. So if you see 0, 1 star over here, you see 0, 1 star over here, versus you see 1, 0 star over here. Also you see 1, 0 star over here. We can do something that you very used to in algebraic expression. Okay, so what can I do? So this one, for example, tells me that the orange one tells me I can this will be as if I put epsilon here, right? I can either do 1 or epsilon followed by 0, 1 star, basically, right? 0, 1 star is always at the end. However, the front can either be 1 or epsilon, right? Okay. So that one there is going to be either 1 or epsilon. And then I can say 0, 1 star. Okay, that's what I can put. And similarly for the second one, I mean the pink one. You can see I got 1, 0 here and 1, 0 here. So this start with 0, this will be as if I started with epsilon. So I can either go for 0 or epsilon, followed by this pattern here. So it could be either 0 or epsilon, followed by 1, 0 star. And then I can put a plus in the middle. Okay, so you can think about version 1 and version 2. And version 2. Both are correct, but if there's a requirement that you should really make as few characters as possible in your regular expression, maybe version 2 will be the way to go, right? All right, that's the one. Okay, let's now move on. Okay, so that's the one, and you will see exactly the reasoning that I went over with you. And these are something you guys can try, okay? Different regular expression that you can try, okay? Some of them we're also going to take to see how we can build the DFA or NFA for them, right? Because they are regular languages. As we said, all the notation we're going to go over, they are equally expressive, okay? That's something we'll do. All right, something very quickly about operator precedence. Precedence simply means when you have no parentheses, which operation should really go first? You know, when you do basic arithmetic, multiplication has higher precedence than addition, right? So there's something similar in regular expression. So let's talk about it. Okay, just before that, let me just tell you the rule, okay? In terms, that's also on your slides, but just for us to do the example, I'll do one of them together with you. The other two you can try as exercises. Okay. So the precedence rule. The highest precedent is the cleaning star. And the next one is concatenation. I'll say concat because it's like one followed by the other, right? And then concatenation. And then the union. Think about this is the highest. And this one here is the lowest. When there is no parenthesis, you should go with this particular order. For example, if you look at this one here, there is no parenthesis. How many operations are there for regular expression? We got cleaning star. Also, we got concatenation. We got two of them. When there is no parenthesis, the operator with the higher precedence should really go first. So that means this will be as if we do this one first and then do concatenation, right? Straightforward. So you can think about this one here. It's just equivalent to we do 0 star first and then do concatenation. You'll be as if. And this one here tells us we want to do 1 0 concatenation first before we do cleaning star, right? Apparently, once you use the parentheses to really disambiguate, you can obviously see these two are different. Because for this one here, you try to do cleaning star and then concatenation. This one you do concatenation and then cleaning star. This one you do cleaning star first before you can evaluate the concatenation, right? This one you gotta do concatenation first before you can evaluate cleaning star.
But isn't cleaning star like the top of the
No, we are using parentheses, so now it's different. Whenever you use parentheses, you can somehow overwrite the order.
Let me get this straight. Is cleaning star the
Highest.
highest?
Cleaning star is the highest operator. So here, if you actually have this one here, right? No parentheses. So this one should be done first because that one is higher and concatenation. That's exactly what this one means. But this one here, you use the parentheses to force the order, this one to be done first before the cleaning star.
Okay.
And then, how do you show these two are different? You're basically trying to show that the two sets are different sets, right? So, if you want to show this in general, for example, just draw that in general diagram. Think about this might be the language of regular expression 1. This will be the language of regular expression 2. Okay? Of course, somehow you want to show that the union and the intersection, they are different, right? Or put it in this way. You want to show either over here, you can say either there exists some W such that W is in regular expression 1, but W is not in regular expression 2. You can either show that way, or you can show the other way. As long as you can show one way, that'll be enough. There exists W. W will be a member of the language of regular expression 2, but it is not in the language of regular expression 1. Right? Either way. Guys, let's do one together. And the other two exercises for you. You have a question, or you have the answer to that?
What's regular expression 1 and 2?
Sorry?
What's regular expression 1 and 2?
Just an arbitrary regular expression. I'm saying that if you're given two regular expressions, how do you show that they are different or they are not equivalent? Good.
And is the dot for concatenation?
Which one?
The dot for concatenation?
This one here?
The dot.
The dot?
Orange dot. Okay, never mind.
That's versus.
I'll ask it.
All right, guys, give me one string that's in one but not the other. 100? Yeah, I like it. Yeah, that's pretty good, right? Obvious. Okay, so we call that a witness. Of inequality. For example, 100 is in 10 star, but 100 is actually not in 10 star, right? Because that's supposed to be alternating. All right, good. Just one example, right? Good. And exercises here, okay, for you. So these are exercises. Okay. I think that would be the last point I would like to cover for regular expressions, and we can do just a little bit about DFA, and then we'll definitely dive into it about its formulation specifically on Tuesday, right? So regular expression definitely is not difficult. I mean, we kind of cover, but I can tell you that, of course, if you go to a particular programming language, they might got different patterns you can actually follow, like heuristics, but that's not something we're concerned about. We just talk about the basic operation theoretically. Okay. Why don't we got about 7 minutes, let's cover something. Okay, some stuff. Okay. Okay, so now we are done with the operator, the precedence. Let's now go over some basic concept about DFA. All right, so just in case you forgot, it's deterministic finite automata. Deterministic in the sense that whenever you're reading some input, it's guaranteed you're actually going to move to a particular state. However, if you actually got an idea about NFA, it's going to be a little bit different. So once we get to NFA, I will show to you, right? It's got to be something that's got to be visualized. Right? It's going to accept or recognize some pattern similar to regular expression. We're just going to talk about patternizing the string. For lexical analysis, yep. And then each pattern has a set of satisfying string. So this part here is just consistent with how we define regular expression. Okay, so we got different languages here. For example, the set of string, odd number of zeros, even number of ones. I'm pretty sure you guys have done this, right, in 2001. We're going to do something slightly more challenging today, maybe altogether. And I think that'll be it for today. And we're actually going to do this one here together as a DFA. Why don't we do that? Okay. Okay, and then also this will be something we can do maybe next time. And then this will be just another one, right? So all these are the typical DFAs you can actually specify. I think that all these are the straightforward ones to use DFA. There will be certain patterns that may not be so straightforward to use DFA right away. You might need some non-determinism, like a use NFA. In which case, once you get an NFA, you can somehow convert that into DFA. That's pretty convenient. That's something I'll show to you. So next time, I'll show you some example that may not be so easy to specify using DFA right away. So what you would do is use NFA and then convert that into DFA. That could be one way to go to guarantee correctness. Okay, and DFA can just be turned into executable program. That's something I will talk about next Tuesday, because once you get a transition table for your DFA, you can easily turn that into if then else statements into any programming language. So straightforward. That's exactly what a Antler 4 does. Once you specify your regular expression, which will be turned somehow into DFA ultimately, and that DFA transition table will be generated for its code in terms of if then else. It's a very tedious process, which you don't have to worry as a compiler developer. You don't have to. You should really focus more on the semantic analysis. Okay? Why don't we do this one here just to quickly. All right? I think we have a choice over here. Oh, you know what? This here, what about this will be exercise for you. I'm going to leave it empty. Before that, why don't we go over very quickly, about 4 minutes, let's go over very quickly the basic notion. Okay, and then that'll be it. So let me just go over some very basic notion together with you, just review the term, and this will be exercise for you. You can try to draw the DFA for this, okay? Let's now look at here. So let's say we have a language here, W. W has an odd number of zeros. Very, very simple DFA, but let's just use this simple example here, draw that, and then just review the terminology. Okay? You're going to start somewhere. So we call that this is a starting states. When you got actually some states where you got some label that has no state to originate from. So you know that this is start states. Okay? This is the start states with an unlabeled transition. So when I say unlabeled transition, I really meant right here. This is unlabeled transition, right? That's a transition, it's an arrow, it's incoming to the start state without any label. That means we start from there. There's only a single start state that we assume for DFA, okay? And then you can do as many transitions as you like. So now in this case, we only need just another state. Oh, sorry. Maybe just another state right here. Okay. Oh, sorry. It's not exactly perfect circle. There we go. Better? All right. So you can think about this will be S0 and S1. And usually you can give some very simple name, S0, S1, just starting from 0, like an array. And then you have to set aside some description. So S0 and S1, what does it really mean when you are in this particular state? You're going to want to characterize it very briefly. In S0, for example, when we first start, we haven't processed any input string just yet. We have only read epsilon. Empty string has even number of zeros. Agree? 0 is an even number. Okay? S0 over here, that means we have already read even number of zeros. S1 here would be we have read odd number of zeros. Okay? So now for DFA, deterministic. That means from each state, must have outgoing transitions. Corresponding to the entire alphabets. Corresponding to the entire alphabet. Let's say here we assume we're just reading zeros and ones. That means we should get exactly 2 outgoing transitions. If we have read just 1, that doesn't impact the number of zeros. So 1 here. because we only consider about number of zeros. However, if I have already read even number of zeros, if I read another zero, that should be odd number of zeros, right? So that should be 0 here, all right? And then over here, similarly, so here if I'm only reading 1, there's an impact. But so far, I've read odd number of zeros. If I read another 0, even number of zeros, just transition between odds, even, odd, even. Right, you can see for this state over here, we got exactly 1 and 2 transitions. Here, we got exactly 1 and 2 transition, covering exactly 0 and 1. Okay, one more thing, and I'll let you go. Currently, this DFA here, you're indicating the DFA is not going to accept anything, because there's no state that's going to accept anything. So you want to indicate if the ending state happen to be either one of them, it's going to be accepting. The convention is we're going to make, for example, here we talk about odd number of zeros. So we're going to make one of the states, at least one of the states, double circle. That's so-called final or accepting states. So this is a final or accept states. All right. There should be at least one, at least. All right, I think just about the basic notation over here. And you guys, a little homework or exercise you can try, which we're going to go over as well, is for this particular language. We want to read zeros and ones, but we want to make sure we only accept the pattern if we got equal number of alternating zeros and ones. Got to be equal number. Okay. Thank you so much, and then I'll see you on Tuesday.